Okay, guys, so let's continue with the state space representation. So this is our part 2. So remember our question was how to obtain state space representation for a given transfer function model. Okay, so we will try to answer that with an example, okay, which will lead into one way we can actually do this. Okay, so in our example, the system is given in a factorized form. So this has 1, 0, s minus 4, and in the denominator we have 3 poles, s plus 1, s plus 3, and s minus 2. Okay, now in order to convert this into a state space representation, what we will do is that we will use the partial fraction expansion in order to decompose this into 3 separate terms, one for each pole. So this is going to be equal to alpha 1 over s plus 1, alpha 2 over s plus 3, and alpha 3 over s minus 2. Okay. And I'm going to skip the details of the partial fraction expansion, but using partial fraction expansion, you can verify that we obtain alpha 1 to be equal to 5 over 6, alpha 2 being equal to minus 7 over 10, and alpha 3 being equal to minus 2 over 15. So we assume that we have obtained the partial fraction expansion for this given transfer function. Okay. Now remember that we also know from our derivation is that the transfer function is equal to c times si minus a inverse b. Now we have c, a, and b as unknown matrices in this representation. Now we will consider a proposal. Okay, we will let A be a specific selection, which is just composed of the poles of this system as a diagonal matrix. So our poles are minus 1, minus 3, and 2. So I will just put the poles in the diagonal entries like this. And try to work out the other two matrices, C and B, if we can. Okay, so that's going to be our trial. So let's see what happens with this G of S given this selection of the A matrix. Let's first calculate Si minus A. That's going to also be a diagonal matrix because we have S0, 0. Si matrix is something like this, and minus the A matrix, which is as per our proposal. Okay, and this matrix obviously turns out to be these denominator terms, right? S plus 1, S plus 3, and S minus 2 on the diagonal entries, and the remaining entries being just zeros. Okay, now for a diagonal matrix, what is the determinant of this? Determinant of Si minus A, which is also illustrated as this vertical bars, Si minus A. Okay, and what is this? for a diagonal matrix, the determinant of the matrix is the multiplication of the diagonal entries. So this turns out to be the product of the poles. Remember that this is actually our characteristic equation. Okay, our characteristic equation. Remember that the determinant of Si minus A was actually at the denominator of this expression that we have previously derived. Okay, so that corresponds to our characteristic equation here. Okay, so this is our characteristic equation. Now let us calculate the inverse of this matrix. So Si minus A inverse. Now again, for a diagonal matrix, the inverse is very simple. It's just the inverse of all the diagonal entries. So Si minus A inverse is just composed of the inverses of the diagonal entries as such. And the remaining entries remain as zeros. Okay. So now let us calculate what g of s would be as per this equation that we have previously written. So g of s, which is equal to c times si minus a inverse b, and let the C matrix be composed of C1, C2, and C3, and the B matrix be equal to B1, B2, and B3. The product is actually equal to C1, C2, C3 multiplies this matrix 1 over s plus 1, 1 over s plus 3, 1 over s minus 2, and this also multiplies b1, b2, and b3. Now if you make this multiplication, in fact, you can first multiply the second and third matrices, and then you can multiply it with the first matrix. But you will verify that this will turn out to be, because we have a diagonal matrix in the middle, is that we will have this expression. C1 B1 times 1 over the first pole, s plus 1. C2 B2, 1 over the second term, s plus 3, and C3 B3, 1 over s minus 2. Now from this, remember that we had also obtained that this is equal to alpha 1, 1 over s plus 1 plus alpha 2 times 1 over s plus 3 plus alpha 3 times 1 over s minus 2. So what we obtain, therefore, is that we have C1 B1 equal to alpha 1, C2 B2 equals alpha 2, and C3 B3 equals alpha 3. Now we can see that we can obtain the values of the products of C1, B1, Ci, Bi in general, but we cannot individually obtain C and B. So we can in fact generate infinitely many representations by selecting a particular B and calculating what C should be in return. So if we make a particular selection for B, for example, if we select it to be composed of all ones, what this will result in is that C will be given by the alpha values. Okay, and that's going to be, for our example, it's going to be 5/6 for the first entry, minus 7/10, and minus 2/15 in our example. So the conclusion is that we have obtained, you might call this by trial, because we made a trial for by selecting a particular A. We have obtained a particular state space representation. Now this particular form, as well as some others that we will explore, are actually called canonical representations. Canonical representations. Well, for canonical, with canonical, what we mean is that some special important selections or representations. We already have stated that we might have infinitely many representations, but therefore what becomes important is these particular canonical representations. Okay, now what we have obtained is one of them. So we have obtained what is called the diagonal canonical form. Diagonal canonical form, state space representation. Sorry about that. Representation. So in our example, right, we started with a transfer function. We made a particular choice for the matrix A as being composed of the eigenvalues, as composed of the poles of this system. And we ended up making a choice, a possible choice for C and B. And we were able to determine both A, B, and C. And this one we call the diagonal canonical form. Okay? Now, let me generalize the diagonal canonical form for reference. Okay? Generalization, because we work this on an example. So if g of s is composed of a proper transfer function where the numerator is 1 degree less than the denominator, is the coefficients being b1 to bn, and in the denominator we have a polynomial of degree n, and where the coefficients are a1 to an. And let's say that we can successfully decompose this into its partial fractions. Where pi are the poles of this transfer function using partial fraction expansion. Then we have A being composed of the poles themselves on the diagonal, Pn, and B selected as all ones, and in this case C as being selected as the coefficients of the partial fraction expansion. Okay, so this is the diagonal canonical form in general. So the procedure is that you find the poles of g of s, you expand it into partial fractions, and then you have the state space representation given as indicated. So what is the disadvantage of this? Now the advantage is that you see it's a decoupled form where actually the change in any state only depends on the value of that state and also with the input. Okay, so there is no coupling between the states. A state does not affect another state. Okay, what is the disadvantage? Well, we need to find the poles. Further, poles can be complex conjugate. In this case, we cannot do this. We cannot obtain the diagonal canonical form. Okay. Now I will give you an example. So now I will give you an example where we have complex conjugate poles, and in this case we will be able to very simply obtain the state space representation, but we will need to generalize this because I'm going to also show you some difficulty with this example in a minute. Okay, so here's our example. So example where we have complex poles. So when I have complex poles, I cannot expand it into partial fractions, and I cannot select essentially a diagonal A matrix. In this case, I have no zeros. Okay, and I will show you what's the problem with the zeros in a minute. So here's our g of s is equal to 1 over s squared plus 2s plus 2. Okay, so in this case, I will not worry about finding out what the poles are, but I will do something else. Okay, so we know that g of s is equal to the output divided by the input. So if I cross multiply the terms, I will have s squared plus 2s plus 2 times y of s being equal to u of s. Now if I take the inverse Laplace transform, I will get a differential equation, right? I will have y double dot plus 2 times y dot plus 2 times y is equal to u. Okay? Now let us define the states as being, now because this is a differential equation, right? The variable that is inside the differential equation, y, one of the typical choices, and we have seen this in the mechanical systems, is that I can choose the first state to be y and the second state to be the derivative of y. Okay, now let us see what this gives us. Now obviously by this choice, x1's derivative becomes the derivative of y, so that becomes equal to x2. So that's one of the state equations. And the second state equation is that x2 dot becomes y double dot, and we can obtain y double dot from basically the equation that we have here. Okay, so y double dot is equal to minus 2 times y minus 2 times y dot plus u. Now, obviously, y and y dot are our states, so this also becomes equal to minus 2 times x1 minus 2 times x2 plus u, which is equal to x2 dot. Okay, so that becomes our second state equation for x2 dot. Now let me put or try to put this into a matrix form. So I have x1's derivative and x2's derivative. So here I will have the A matrix, and A matrix will multiply x1 and x2, and plus I will have the B matrix, and this is going to multiply u. Okay, so if we take a look at the first equation, so I have x1 dot is equal to simply x2 with no input term, and the second equation gives me that I have minus 2 times x1 minus 2 times x2 plus u. Okay, and remember, what is my y? What is my y? Y is my x1. Okay, that was my choice for x1. So therefore, the output equation becomes the C matrix times the states x1 and x2. But because y is equal to x1, so I will have simply 1 and 0 here. Okay, so that becomes my state space representation. So that looks really nice, and that doesn't need us to obtain the poles, and we don't care about whether we have complex conjugate poles or not. So where does the problem comes from? Let me give you an example on where the problem appears. Okay, example, with a difficulty. So the difficulty happens when you have zeros. So let us consider the same example, but this time we have a 0 in the numerator. So I have s squared plus 2s plus 2. I try to do the same, y of s over u of s. I cross multiply the terms. So I have s squared y of s plus 2s y of s plus 2 times y of s, and that becomes equal to s times u of s plus 2 u of s. Now what is the difficulty is that if I take the inverse Laplace transform of this, minus 1, right? So I have y double dot plus 2y dot plus 2y, and that is equal to u dot plus 2u. Now unfortunately our state space representation does not or cannot have any derivatives of the input. That's simply not possible. Okay, not possible in the state space representation. Okay, so therefore we cannot select the states as per our previous selection as y and y dot. In fact, I'm going to show you in a minute that in this case we need a much more complicated state selection in order to be able to somehow merge this derivative of the input inside the state. so that we can derive state space representation. Okay, so now as our last kind of discussion for this video, let's try to generalize this problem and obtain a canonical form as a result, and this will turn out to be the controllable canonical form. Okay, so controllable canonical form will result from the general case. Okay, so what is the general case? Let me write it down. In the general case, we have g of s, the ratio of y of s to u of s, and is given by our usual rational form. Okay, 1 degree less in the numerator, s to the power n plus a1 s to the n minus 1 plus dot 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 an. Now let me call this denominator polynomial as q of s. So let me cross multiply the terms again. So what I'm going to have is that, okay, let me not cross multiply, but use q of s in my equation. So what I will have is that y of s will be equal to b1 s to the power n minus 1 over q of s, u of s. In fact, it's a cross multiplication, or at least partial cross multiplication, plus, so this is capital U of s, right? Plus b2 s to the power n minus 2 over q of s. So q of s is in the denominator for each case, plus up to bn 1 over q of s u of s. Now here's the interesting part, and it's by no means trivial, is that I will define this term over here as my first state. Okay, so this is going to be x1 of s, and this is going to be defined as x n minus 1 of s, and finally this term over here will become, or will be defined as xn of s. Are the state selections. So let's see what this gives us in terms of state space equations. Okay, so now what we have is that, take a look. Now the relationship between x1 of s and x2 of s is nothing but an extra s. Okay, so x2 of s is s times x1 of s. Okay, so x2 of s is equal to s times x1 of s. So what does that tell me? Well, I know that x2 of t therefore is x1 dot of t. Okay, and similarly for the others, except for xn of s. Okay, in fact, not xn of s, but okay, not okay. So similarly for in fact for all others. Okay, so let me write them down here. So I have x1 dot is equal to x2, x2 dot is equal to x3, up to xn minus 1 dot being equal to xn. But the only problem here that I have is that I don't have xn dot. Okay, so I need to take care of this. How to obtain this final equation, state equation. Okay, so let's try to do this. Okay, let me try to take the Laplace transform. So take the Laplace transform. So what becomes is that s times xn of s. So because I have xn of s given by this term, s to the power n minus 1, right, over here, s times xn of s is equal to s to the power n over q of s times u of s. And since this is s to the power n times u of s over q of s, and this is equal to x1 of s. So this is equal to s to the power 1, s to the power n, x1 of s. Now we need to obtain what this is. Okay? So we will now try to write this term, s to the power n, x1 of s, as a linear combination of all the states. Okay, that's what we need to do. Let us write the definition of our x1 of s. So that is 1 over q of s times u of s. Okay, and that means we have q of s times x1 of s is equal to u of s. Remember what was q of s? Q of s was s to the power n, a1 s to the power n minus 1 up to an times x1 of s, and that is equal to u of s. Now if I expand this, in fact you get the term s to the power n x1 of s, which we were after, but we need to continue with all the terms. A1 s to the n minus 1 x1 of s up to an x1 of s, and that is equal to u of s. Now if I leave s to the power n x1 of s alone on the left hand side, what I'm going to get is a linear combination of all the other states, and let's actually show it. Okay, minus a2 s to the n minus 2 x1 of s minus up to minus an x1 of s plus u of s. Now let us remember our definitions for the states. You see that in fact what we have is that if this term is x1 of s, you see that xn of s actually is s to the power n minus 1 times x1 of s. So in fact, therefore, this term here is xn of s. This term here is xn minus 1 of s. And this term here obviously is x1 of s. Okay? So in fact, if I go back to the time domain to write my state space equation, so this becomes, and in fact, from the beginning, this was equal to xn dot of t, and that is equal to minus a1 xn. Now everything is a function of t, right? Xn of t minus a2 xn minus 1 of t minus up to minus an x1 of t plus u of t. So that is, so if these are my state equations, right? The first state equation, the second state equation, n minus first state equation, and now what we have here is the nth state equation. Okay. The final state equation. Mind you that in this equation I only have a linear combination of all the states, and I also have only the input term, and no derivatives are involved. So let us put this into basically the matrix form and finish for this session. Put into matrix form. And basically what I have is that the derivative of the states xn dot, okay, so the derivatives should be apparent here. So x1 dot, so here I have the states up to xn. Also, I need to have the inputs. So now x1 dot is equal to x2. So what I'm going to have here is 0, 1, 0, and all zeros. x2 dot is equal to x3. So I will have 0, 0, 1, and then all zeros. In the next to last row, I will have 0, 0. So xn minus 1 will be equal to xn. So this is going to be 0 and 1. And in the final row, so no input terms for none of these equations. And in the final row, I will have minus an. You see, minus an times x1 of t. So minus, let me put it here, minus an minus an minus 1, and finally minus a1. Okay, sorry about this. Let me write this again. Minus an minus 1 minus a1. Okay, right here I'm a bit squeezed with my resolution here, and also I have here the input term. Okay. What about, what is the output y of t? Okay. So if we go back over here to our initial equation, you see this is the expression for the output, right? It's a linear combination of all the states where coefficients are b1, b2 up to bn. Okay. So so we had y of s equals b1 xn of s, b2 xn minus 1 of s up to bn x1 of s. And if we go back to the time domain, y of t is b1 xn of t up to bn x1 of t. Okay, so it's a linear combination of all the states. So my final equation here is that y is equal to basically bn minus 1 up to b1 times the states x1, x2, xn. Okay, so if I wanted to just indicate my state equation, that's that is these are the state equations, and this is the output equation of my state space representation. So this is the so-called controllable canonical form. Controllable canonical. Well, you might be wondering why it's called the controllable canonical form. Well, we will show that it's going to be related with a property called controllability, and that's going to be eventually relate to being able to design a controller, a state feedback controller for this state space system. Okay, so let's break here and we will continue in the next video.